4 presentations. The first one is Mr. Wei Zheng. He comes from the School of Transportation and Science Engineering of Beihang University. His research interest is vehicle transmission and control technology. His topic is about detection and diagnosis of speed sensor air gap change fault. So let's welcome the Zheng.
Good morning, everyone. I'm Zheng Wei, and I'm very honored to be able to participate in this conference. The topic of my presentation is detection and diagnosis of the speed sensor air gap change fault. My presentation mainly includes the following 4 parts. Hall-type speed sensors are commonly used in automatic transmissions. It works by principle of Hall effect. When the tooth tip of the speed measuring gear is close to the Hall sensor, the magnetic flux is concentrated through the metal gear, and the sensor outputs an electrical pulse signal. The speed is obtained by calculating the frequency of the pulse signal. The air gap between the tooth tip of the speed measuring gear and the speed sensor should meet certain installation requirements to make sure the speed sensor works normally. But in actual work, the gear is impacted by the concerning changing torque, which changes the air gap between the tip of the speed measuring gear and the speed sensor. The magnetic flux is reduced, and the speed measuring signal is faulty. In order to detect and diagnose the fault, a solution was designed. Collect the speed signal of the Hall-type speed sensor and input the signal into the filter module. By comparing the signals before and after filter ring, a residual generator is designed. And an adaptive dynamic threshold can configure a reliable and effective threshold in real time. If the residual signal exceeds the threshold, it means that a fault has occurred. After confirming the fault has occurred into the debounce module, the function of the debounce module is to prevent false alarms. If the fault is confirmed as the final fault in the debounce module into the fault handling module. The main purpose of filter ring is to remove the interference of the fault signal and the losses of the sensor itself, and smooth the speed signal. In view of the characteristics of the fault, firstly, the signal is practiced by limiting filter module to remove the interference of the fault signal. The filter effect is shown in the figure. We can see that the limiting filter can effectively remove the fault signal interference. The speed signal after the limiting filter still needs to be performed again to smooth. By comparing the effect of low-pass filter and Kalman filter, the most suitable method is chosen. 2 methods are used to filter the signal by the same segment of the speed sensor. The difference between the filter signal and the original signal are being the respective residuals of the 2 methods. In order to make it easier to observe the trend of the residual change, mean filter ring is performed, as shown in the figure. It can be seen that Kalman filter has a better effect when the trend of the speed signal does not change. But the effect of the Kalman filter is poor when the trend of the speed signal changes. The Kalman filter needs to establish an accurate system model, which is generally suitable for linear system, but automatic transmission is nonlinear and complex system. The effect of Kalman filter is not ideal, and the application effect is poor. Although low-pass filter has a big luck when the filter coefficient is too small. By selecting a suitable filter coefficient, a better filter effect can be achieved. Therefore, considering the advantage and disadvantage of the two methods, low-pass filter method is successed to smooth the speed signal. The filter module is composed of a limiting filter module and a low-pass filter module. The limiting filter module is responsible for removing the fault signal interference, and the low-pass filter module is responsible for smoothing the speed signal. The design of the adaptive dynamic threshold is to generate a reliable threshold in real time by analyzing the factor of the residual. Compared with a fixed threshold, the robustness and effectiveness are improved. By passing the residual signal through the mean filter ring, the trend of the residual can be obtained more clearly. By comparing the trend of the residual with the undertalk in the system, there is a high positive correlation trend between the residual and the undertalk as shown on the left. It shows that greater the torque output by the under, the greater the vibration of the automatic transmission system, and the greater the residual. The filter coefficient of low-pass filter indicates the degree of filter ring. The smaller the filter coefficient, the greater the degree of filter ring. By comparing the residual and different filter coefficients, there is a negative correlation with the filter coefficient, as shown on the right. In addition, the speed sensor itself also has measurement error, which is also an important factor. The final dynamic threshold is shown in the figure. The purpose of deboning is eliminating occasional and resemble faults and avoid false alarms. Only when the number of times the fault confirmation flag is activated reaches the fault final confirmation, or the duration of activation reaches the final confirmation timing. The final confirmation flag is activated, and the fault is determined to be the final fault. The method introduced in this paper is used to forecast the real output shift speed signal of automatic transmission. Firstly, the original signal is forecast by limiting and low-pass filter. The original signal and the filter signal are shown on the left. By making the difference between the speed signal before and after filter ring, the residual is obtained. At the same time, according to the design dynamic threshold, the threshold value is generated. The residual signal and the dynamic threshold are shown on the right. From the figure, it can be seen that the speed signal is in normal state at 0 to 50 seconds. The residual signal is always less than the dynamic threshold, and the dynamic threshold starts to appear at about 50 seconds. Once the residual of the fault signal exceeds the dynamic threshold, the design dynamic threshold can effectively detect the fault. If the residual of the fault signal exceeds the dynamic threshold, it means that a fault has occurred, and the fault flag is activated. According to the characteristic of the fault signal, the fault confirmation timing is set to 1. Once the fault signal residual amplitude exceeds the dynamic threshold, the fault confirm flag will be activated. Due to the short occasion of fault signal, the setting is confirmed based on the number of duration of fault. Set the final confirmation of the fault equal to 5. If the number of fault occasions is greater than or equal to 5, the fault is finally confirmed. The simulation result of the fault debound signal is shown in the figure. All the residual of the fault signal exceeds the dynamic threshold are recorded next. And the fault flag is activated. Once the fault flag is activated, the fault confirm code is increased 1. When the fault confirmation reaches 5 times, the fault is confirmed as an unrecoverable fault. Let's make a conclusion. The simulation is pressing when the method perfect effectively. The solution can effectively detect and diagnose this type of fault. It also has the following aspects that can improve. Building an extended Kalman filter based on the nonlinear momentum of automatic transmission and varying the filter effect. Applying the method to the bench test or hardware in-loop simulation in the automatic transmission system. That's all my presentation. For more details, welcome to contact me by emails. Thank you for listening.
Thanks for your presentation. Is there any question?
Thank you for your presentation, Mr. Zheng. You mentioned no pass filter in your presentation, and we know that the low pass filter has the characteristic of lag. And how you reduce the impact of lag in your work? Can you explain this for us?
If the filter coefficient is too small, it will cause a big lag. If the coefficient is too big, it will reduce the effect of filtering. So we need to choose a suitable filter coefficient to reduce the impact of the lag and at the same time to get the effect of filtering we need.
Okay, and I have another question. In the debonus module in your work, why you take the number of fault as the standard or as the basis of its final recoverable fault?
The character of the fault is short duration and large amplitude. It's difficult to record it like better generation of the fault. So we have to judgment it by better time of it.
Okay, thank you.
Any question? So thank you for presentation again, and we will have a present for you.